Hi everyone, welcome to Code Karle. In this video, we'll be looking at another very common design interview problem, which is to design a e-commerce application, something very similar to Amazon or Flipkart or anything of that sort. Now, let's look at some functional and non-functional requirements that this platform should support. So the very first thing is that people should be able to search for whatever product they want to buy. Okay, and along with searching, we should also be able to tell them whether we can deliver it to them or not. So let's just say a particular user is in a very remote location where we cannot deliver a particular product, then we should clearly call it out right on the search page. Why? Because let's say if the user has seen 100 products and then they go to checkout flow, add into cart, and then if we tell them that we can't deliver, then that's a very bad user experience. So at the page of search itself, we should be able to tell them that we cannot deliver, or if we are delivering, by when should we be able to deliver it to you. The next thing is there should be a concept of a cart or a wish list or something of that sort, so that people can basically add a particular item into a cart. The next thing is people should be able to check out, which is basically making a payment and then completing the order. We will not look at the how the payment exactly works, like the integration with gateways and all of that, but we'll broadly look at how the flow overall works. The next thing is people should be able to view all of their past historical orders as well. The ones that have been delivered, the ones that have not been delivered, everything. From the non-functional side, the system should have a very low latency. Why? Because it'll be a bad user experience if it's slow. It should be highly available and it should be highly consistent. Now, high availability, high consistency, and low latency, all three together sounds a bit too much. So let's break it down. Not everything needs to have all these three. So some of the products which are mainly dealing with the payments and inventory counting, they need to be highly consistent at the cost of availability. Certain components like search and all, they need to be highly available, maybe at the cost of consistency at times. And overall, most of the user-facing components should have a low latency. Now, let's start with the overall architecture of the whole system. We'll do it in two parts. First, we'll look at the home screen and the search screen, and then we'll look at the whole checkout flows. Okay. And before we get to the real thing, let's look at a bit of convention to start with. Things in green are basically the user interfaces, could be browsers, mobile applications, anything. These two are basically not just load balancers, but also reverse proxies and authorization and authentication layer in between that will authenticate all the requests that are coming from outside world into our system. All the things in blue that you see here are basically the services that we have built, could be Kafka consumers, could be Spark jobs, could be anything. And the things in red are basically the databases or any clusters, could be Kafka cluster, Hadoop cluster, or any public facing thing that we have used. Okay. Uh, Now let's look at the user interfaces, what all we'll have. So we'll mainly have two user interfaces here. One is the home screen, which would be the first screen that a user comes to. It would by default have some recommendations based on some past record of that user, or in case of new user, some general recommendations. In case of search page, it would just be a text box wherein user can put in a text and we'll give them the search results. With that, let's look at how the data flow begins. So a company like Amazon would have various suppliers that they would have integrated with. Now these suppliers would be managed by various services on the supplier front, right? I'm abstracting out all of them as something called as an inbound service. What that does is basically it talks to various supplier systems and gets all of the data. Now let's say a new item has been coming, or a supplier is basically onboarding a new item. That information comes through a lot of services and through inbound service into a Kafka. That is basically a supplier world coming into the whole search and user side of things. Now there are multiple consumers on that Kafka which will process that particular piece of information to flow into the user world. Now let's look at what that is. So the very first thing that will happen is basically something called as an item service. So item service has a lot of people talking to it, and if I start drawing all the lines, then it become too cluttered. So I've not drawn any connection to item service, but item service will be one of the important things that listen to this Kafka topic. And what it does is it basically onboards a new item. Now, it also is basically the source of truth for all items in the ecosystem. So it will provide various APIs to get an item by item ID, add a new item, remove an item, update details of a particular item. And it will also have an important API to bulk get a lot of items. So get API with a lot of item IDs, and in response, it gives details about all of those items. Now, item service sits on top of a MongoDB. Now, why do we need a Mongo here? So item information is fundamentally very non-structured. Different item types will have different attributes, and all of that needs to be stored in a queryable format. Now, if we try to model that in a structured form in a MySQL kind of a database, that will not be an optimal choice. So that's why we've used a Mongo. To take an example, let's say if you look at attributes of some products like a shirt, it would have a size attribute and it would probably have a color attribute, right? Like a large size t-shirt of red color. If you look at something like a television, it'll have a screen size saying a 55-inch TV with a LED display kind of a thing. There could be other things like bread, which could have a type and a weight, like 400 grams of bread, of which is of wheat bread or a sweet bread or something of that sort. So it's a fairly non-structured data, and that's the reason I've used a Mongo database here. Now, coming to other consumers that will be sitting on that Kafka. So on this Kafka, there's something called as a search consumer. What this does is basically whenever a new item comes in, this search consumer is responsible for making sure that item is now available for the users to query on. Okay, so what it does is all the items that are coming in, it basically reads through all of those items. It puts that in a format that the search system understands, and it stores it into its database. Now, search uses a database called Elasticsearch, which is again a NoSQL database, which is very efficient at doing text-based queries. Now, this whole search will happen either on the product name or product description, and maybe it will have some filters on the product attributes. Those kind of things is something that Elasticsearch is very good at. Plus, in some cases, we might also want to do a fuzzy search, which is also supported very well by Elasticsearch. Now, on top of this Elasticsearch, there is something called as a search service. This search service is basically an interface that talks to the front end or any other component that wants to search anything within the ecosystem. It provides various kinds of APIs to filter products, to search by a particular string or anything of that sort. And the contract between search service and search consumer is fixed. So both of them understand what is the type of data that is stored within Elasticsearch. That is the reason consumer is able to write it and the search service is able to search for it. Now, once a user wants to search something, uh, there are two main things around it. One is basically trying to figure out the right set of items that needs to be displayed, but there's also one important aspect that we should not show items that we cannot deliver to the customer. So, for example, if a customer is staying in a very remote location, and if we are not able to deliver big size items like a refrigerator to that pin code, we should not really show that search result to the user as well, because otherwise it's a bad experience that he'll see the result, but he'll not be able to order it, right? So search service talks to something called as a serviceability and patch service. Okay, this basically does a lot of things. First of all, it tries to figure out that where exactly the product is, in what all warehouses. Okay. Now, given one of those warehouse or some of those warehouse, it tries to see, do I have a way to deliver product from this warehouse to the customer's pin code? And if I have, what kind of products can I carry on that route? Now, certain routes can carry all kinds of products, but certain routes might not be able to carry things like big products or other kind of products, right? So all of those filtering stays within the serviceability and tax service. Now it also does one more thing, that it tells you in how much time I'll be able to deliver. Okay. So it could be like in number of hours or days or anything of that sort. It can say that probably I'll be able to deliver it in 12 hours or 24 hours or something of that sort. Now if serviceability tells that I cannot deliver, search will simply filter out those results and ignore that and return the rest of the remaining things. Okay. Now search might talk to user service. There's something called as a user service here. We'll get into that later on. But user service is basically a service that is the source of truth of all the user data. And it can query that to fetch some attributes of user, probably a default address or something of that sort, which can be used, basically which can be passed as an argument to serviceability service to check whether I can deliver it or not. Okay. Now, search service returns the response to the user, which can be rendered, and the people can see whatever they want to see. Now, each time a search happens, an event is basically put into Kafka. The reason behind this is whenever somebody is searching for something, they're basically telling you an intent to buy a kind of product, right? That is a very good source for building a recommendation, right? We look at how recommendation can be built later on, but this is an input into recommendation engine, and we'll be using a Kafka to pass it along. Okay, so each search query goes into Kafka saying this user ID search for this particular product. Now, from the search screen, user could be able to wishlist a particular product or add it to cart and buy it, right? All of those could be done using the wishlist service and cart service. Wishlist service is the repository of all the wishlists in the ecosystem, and the cart service is a repository of all the carts in the ecosystem. Carts are basically shopping bags, which when people buy, put product into it and then check out. Okay. Now, both these services are built in exactly same way. They provide APIs to add a product into user's cart or wish list, get a user's cart or wish list, or delete a particular item from that. Okay, and they would have a very similar data model, and they are both sitting on their own MySQL databases. Now, from a hardware standpoint, I'd like to keep these two as separate hardware, just in case, for example, wishlist size becomes too big and it needs to scale out, so we can scale this particular cluster accordingly. Okay, but otherwise, functionally, both of them are totally same. Now, each time is person is putting a product into wish list, they are again giving you signal. Each time they are adding something into their cart, they are again giving you a signal about their preferences, things that they like, that they want to buy, and all of that, right? All of those could again be put into Kafka for a very similar kind of analytics. Now let's look at what those analytics would be. So from this Kafka, there would be something like a Spark streaming consumer. One of the very first things that it does is kind of come up with some kind of reports on what products people are buying right now. Okay, those could be things like coming up with a report saying what was the most bought item in the last 30 minutes, or what was the most wishlisted item in last 30 minutes, or in electronics category, which product is the most sought after product. So all of those could be inferred by this Spark streaming, right? Other than that, it also puts all the data into Hadoop, saying this user has liked this product, this user has searched for this product, anything that happens, right? On top of it, we could run various ML algorithms. I've talked about those in detail in another video, but the idea is given a user and a certain kinds of products that they like, we could be able to figure out two kinds of information. One is what other products this user might like, okay? And the other thing is how similar is this user to other users, and based on products that other users have already purchased, we would recommend a particular product to this user. Okay, so all of those is calculated by this Spark cluster, on top of which we can run various ML jobs to come up with this data. Okay, once we calculate those recommendations, this Spark cluster basically talks to something called as a recommendation service, which is basically repository of all the recommendations, and it has various kinds of recommendations. One is given a user ID, it will store general recommendations saying what are the most recommended products for this user, and it will also store the same information for each category, saying for electronics for this user, these are the recommendations. For in the food kind of a thing for this user, these are the recommendations. So when a person is actually on home page, they'll first see all in the general recommendations, and if they navigate into a particular category, they'll see the specific recommendations which are specific to the category. Now we have skipped a couple of components. User service is a very straightforward service, which basically you can look at any other of my videos where I've talked about it in detail, but it's a repository of all the users. It provides various APIs to get details of a user, update details of a user, and all of that. It will sit on top of a MySQL database and a Redis cache on top of it. Now let's say search service wants to get details of a user. The way it will work is it will first query Redis to get the details of the user. If the user is present, it will return from there. But if the user is not present in Redis, it will then query a MySQL database, one of the slaves of that MySQL cluster, get the user information, store it in Redis, and return it back. So that's how user service will work. Now there are some other components that are here. One is logistic service and one is warehouse service. Normally, these two components come in once the order is placed. But in this scenario, this serviceability service might query either of these two services, not at runtime, but to before catching the information to fetch various attributes. So for example, it might query this warehouse service to get a repository of all the items that are in the warehouse, or it might query logistics service to get details of all the pin codes that are existing, or maybe details about all the courier partners that work in a particular locality. And all of the information, this serviceability service will basically create a graph kind of a thing saying what is the shortest path to go from point A to point B and in how much time can I get there. Now, we have not covered this service in detail. I've also made another video on implementation of Google Maps. This is very similar to that. And also, so if you want to get into details, you can look at that. But just to call it out, this doesn't really do any calculation at runtime. It will store all the information in a cache, and whenever anybody queries, it will query the cache and return the results from the cache itself, and no runtime calculation, because those kind of calculations are fairly slow, and it will calculate all possible requests that can come to it. Basically, if there are n pin codes and m warehouses, it will do a m cross n and calculate all possible combinations of requests that can come to the service and store it in the cache. Now, let's look at what happens when a user tries to place an order. So the user interaction to place an order is represented as this user purchase flow. This could be accessed through apps, mobile apps, or web browsers, or anything. Now, whenever user says that I'm ready to place an order, take me to the payment screen, which is the last piece in the app flow, then basically the request goes to something called as a order taking service. Think of order taking service as a part of order management system which takes the order. Now, order management system sits on top of a MySQL database. Why MySQL? Because if you look at order and the table form for order, it'll have a lot of tables, some with order information, some with customer information, some with item information. And there are a lot of updates that happen onto the order database, right? For each order. Now, we need to make sure that those updates are atomic and they can form a transaction so as to make sure that there are no partial updates happening. And because MySQL provides that out of the box, we would leverage that here. So that's why MySQL. Now, whenever this gets called, the very first thing that happens is a record gets created for an order ID gets generated. Now, what the next thing that we do is we put an entry into this Redis saying this order ID was created at some point in time and this record expires at some point. Why is it being used? We'll come to. But think of it as an entry that goes in something like order ID O1 gets placed at 10:00, let's say. It expires at 10:05, something of that sort. Okay. Now the record that goes into this MySQL database has an initial status. Think of it as a status of created. So basically the record that goes into this table is something like order 1 was created at 10:00 with status created. Okay, you can have different set of names also, that's fine. Now, the third thing that happens is we basically call inventory service. The idea of calling inventory service is we want to block the inventory. So let's say if there were 5 units of a television that a user wanted to purchase, we will reduce the inventory count at this point in time and then send the user to payment. Why do we do that? Let's just say there was just one TV and 3 users want to come in at the same time. Now we want to make sure only one of them buys the TV and for two of them it should show that it is out of stock, right? We can easily enforce that through this inventory service by having a constraint onto the table which has the count column saying that count cannot go negative. Now each time you basically want to place that order for a TV, so only if the count is one, only one of the users will be able to do that transaction where the count reduces. For the other two, it will be a constraint violation exception because the count cannot be negative, right? So only one of them will go through with the inventory right. Now, once the inventory is updated, then the user is taken to something called as a payment service. Think of it as an abstraction over the whole payment flow, wherein this service talks to your payment gateways and takes care of whole of the interaction with the payment. Okay, we'll not go into details of how that works, but the interaction with the payment service can lead to two, three outcomes. One of them is that payment service could come back saying the payment was successful, or it could say that the payment failed due to some reason, could be a lot of reasons, or the person could just close the browser window after going to the payment gateway and not come back, in which case payment service would not give a response. So there are these three possibilities. Now let's see what can happen. Okay, so one of the very first thing that can happen is, let's just say at 10:01 we got a confirmation from payment saying payment was successful. In that case, it'll the order would get confirmed, right? So let's say we call it that status is now placed, or any other name for that matter, right? So now once the payment has been successful, we update the status of the order over here in the database saying that order is placed. Now the work is done. At that point in time, an event would be sent into Kafka saying an order has been placed with so and so details, right? Another option, it could payment service could come back saying that or the payment failed. Let's say there was no money in the account or whatever happened, right? Now, once the payment has failed, we need to do a lot of things. First of all, we need to cancel the order because the payment has not happened. So let's say the other possible scenario is the order could be cancelled, right? Now, if the payment has failed, we need to increment the inventory count again. So we'll basically again call inventory service and saying that you decremented the quantity for this particular order ID. Now let's increment it back. So that's a rollback transaction kind of a thing that is happening here. Okay. So that is one more thing we'll do. And also we'll have a reconciliation service that sits on top of this whole system, which reconciles, basically checks every once in a while that if there were 10 orders overall, do I have the correct inventory count at the end, just to handle cases where due to some reason we missed update of inventory count or the write failed. So all of those scenarios can be handled by that reconciliation flow. Now there is one more scenario that can happen. Payment service could not at all come back, right? The user closed the browser window, the flow ends there, payment service doesn't respond back to us. Now what do? We can't keep the inventory blocked. So let's say there was just one television available. This user has gone to the payment screen, closed the window and gone away. Now we still have that one television physically available in our warehouse, but the database says it's not available. We need to bring it back, right? So for that, the Redis comes in. So at 10:05, what will happen is Redis, this record will get expired, right? Redis will have a expiry callback on top of Redis, which will basically be invoked saying that this particular record, whatever you inserted, it has got expired. Now do whatever you want. At that point in time, order taking service will catch that event and say that now this particular record has expired. I'll basically follow the same flow that was followed for payment cancellation. Basically, I'll time out the payment and mark it cancelled. Okay. So at that point in time, again at 10:05, this order would be moved to cancelled state in the database and the inventory would get updated back again. Right? So everything is good. But there are a couple of scenarios here. So there could be potential race conditions. What happens if your payment success event and your expiry happens at the same time? What do you do then? So there are three scenarios in which it could happen. The first scenario is that payment success comes first and then expiry happens. So in that is a scenario that will always happen. So whenever a payment is success, let's say at 10:01 payment got success. Anyway, at 10:05 this expiry would have happened, right? So this is something that is bound to happen for all the orders, right? So one optimization we could do here is each time we get a payment success or payment failure event, we can delete the entry from Redis so as to make sure that expiry event does not come in, right? The other scenario is that expiry comes first and then payment success. Now, whenever we would have got, let's say expiry came at 10:05 and payment success happened at 10:07. Now, whenever we get the expiry event, we would have cancelled the order. We would have decremented the inventory count, right? But now the payment has happened. That we got to know. There we could do two, three things. We could either refund the money back to the customer, saying that for whatever reason we were not able to process, here's your money back. Alternatively, we could also say that now we've anyway got the money from the customer. We know what the person was trying to order. Due to an issue on our side, possibly the order didn't go through. So we could create a new order, mark this payment for that order, and then put that directly into place status. So that is another thing that we could do, right? Now, assuming for all the orders, as soon as we get a payment success and payment failure, we'll delete this entry from Redis so as to make sure there are no these conditions don't happen too frequently. Plus, that will help us to save the memory footprint as well, because the lesser amount of Redis data we have in Redis, the lesser RAM it will consume, and it will be much more efficient. Okay. Now, one thing I want to call out about this Redis expiries is this is not very accurate. So let's say if it was supposed to expire at 10:05, we might not get the callback exactly at 10:05. We might get a callback at 10:06, 10:07, or sometime after 10:05. And that is because of the way Redis expiry works. So Redis doesn't expire all the records at that point in time. It basically checks all the records every once in a while for expiry, and whenever it finds some of the keys that are expired, then it expires that. So it might so happen that it will expire after a few minutes. Now in this scenario, it doesn't really matter. So I think we should be okay with this kind of an approach. But if you're trying to do something which is much more mission critical, then possibly you might have to do a different approach. Okay, but even you should talk to this about your interviewer, and if they say, then you might also change the implementation a bit. You might implement a queue and keep polling that queue every second or something of that sort. Okay, now once the payment has happened or not happened or whatever happened, you would put all of those events into Kafka anyway. There is one more reason why you want to put those events. So let's say there was just one item, one television left. Okay. And somebody has purchased that. Now you want to make sure that nobody else is able to see that television, because anyway the inventory count has become zero. You cannot take an order, right? So you need to basically make sure that it should be removed from search. Now remember, there was a search consumer that we looked at in the previous section. That search consumer would also take care of inventory kind of things. So as soon as an item goes out of stock, it would basically remove that element from the listing. Basically, it will remove the documents pertaining to that particular set of items. Now, there is one problem in this whole thing that we have decided built. This MySQL can very quickly become a bottleneck. Why? Because there are a lot of orders. So for a company like Amazon, they'll probably have like millions of orders in a day, a couple of millions at least, right? And that number could bloat up significantly over an year. And normally you would have to keep order data for a couple of years for auditing purposes, right? So this database is going massively big. We need to do something about it. So remember, the whole use case of having this MySQL is to take care of atomicity, transaction, basically asset properties for orders that are being updated. But for the orders that are not being updated, we don't really need any of these functionalities, right? So what we can do is, once the order reaches a terminal state, let's just say an order is delivered or cancelled, we can basically move it to Cassandra. So there is something called as archival service, which is a cron kind of a thing, which runs every 1 day, 12 hours at some frequency, and it pulls all the orders which have reached their terminal status from this MySQL and puts it into Cassandra. Now, how does it do that? So you can see these two services. There's the order processing service and there's a historical order service. These two are again component of the whole larger order management system, which do certain things of their own. So order processing service is the service which takes care of the whole life cycle of the order. So once the order has been placed, any changes to that order happen through this. This will also provide APIs to get the orders if somebody wants to get order details. Again, similarly, historical order service will provide all kinds of APIs to fetch information about historical orders. Okay. Now, archival service will basically query order processing service to fetch all the orders who have reached terminal status, get all of those details, call historical order service to insert all of those entries into its Cassandra. And once it has got a success saying I've inserted into Cassandra, replicated in all the right places, then it will basically call order processing service to delete that. Let's say there's some error, something breaks in between, it will retry the whole thing, and because it is idempotent, it doesn't really matter. We can replay it as many number of times as we want. Cool. Now coming to the once the user has placed the order, all of the things will happen, logistics and all can happen behind the scenes. Now the user can go and see their past orders, right? That will be powered by this orders view. So orders view will basically, there'll be a service here which kind of is the backend of orders view, but let's not, that will clutter the diagram too much. Assume there's a service here which talks to this order view, and that talks to these two services. So basically what it will do is it will basically query order processing service to fetch information about all the live orders who are in transit, It will call historical order service for all the orders that have been completed. It will merge the data and it will return back to display on the app or website or wherever. Cool. Now, why did we use a Cassandra here? So historical order service will be used in a very limited set of query patterns. There could be orders for a particular. So some of the queries that will run is get information of a particular order ID, or get all the orders of a particular user ID, or possibly get all the orders of a particular seller. But there will be a small number of queries that will run on this Cassandra. And Cassandra is very good when you have that finite number of queries but a large set of data. So that's the reason we've used Cassandra. Good. Now, coming to whenever an order is placed, we want to notify the customer that your order has been successfully placed. It will be delivered to you in 3 days or something of that sort. You'll have to possibly notify a seller. You might have to notify somebody else when something happens, right? Let's say an order is cancelled by the seller, you want to notify the customer. So all of those notifications would be taken care by this notification service. Think of it as an abstraction which can abstract out all various kinds of notifications like SMSs, emails, and all of that. I've made another video which talks about in detail of how to implement notification service, so you can go have a look at that as well. Now, while a user is placing all the orders, all of those things are happening, all the events are going into this Kafka on which we are running a Spark streaming consumer. It does a lot of things. One of the very first things that it does is it can publish a report saying in the last 1 hour what are the items which have been ordered the most, or which category has generated the most amount of revenue, like electronics or food or something of that sort, right? So it can publish out some of the reporting metrics that we want to quickly look at. Other than that, it will also put the whole of the data into a Hadoop cluster. Now we have real order information of a user, which is a very good thing for recommendations, right? So on top of it, we'll have some Spark jobs which will run some very standard ALS kind of algorithms, which would be predicting that this particular user, given that he's ordered certain things in the past, what are the next set of things that this person might order, right? Or because this customer looks like that customer and that customer ordered so and so product, so this customer might also order so and so product. So there could be a lot of kind of models that you can run to predict what are the right set of recommendations for this user, which would be then sent to this recommendation service which we looked at in the last section. It will store it into its Cassandra, and the next time when the user comes in, we'll show them those kind of recommendations. It would not just have like recommendations based on your orders, but also similarity. So again, taking the same example, if you have ordered a whiteboard, you will definitely want to order marker. So all of those things would also be taken care by this. So yeah, I think that should be it for a Amazon kind of a system. Thanks for watching this video. If you have any suggestions on what videos we should make next or how we could improve this one, do let us know by commenting here. And don't forget to subscribe to this channel, like the videos, and share the videos with your friends while we keep working to get more such content to you. Happy learning!